Oh, world. I assume y'all. Please be sure you're putting your names in the chat. Video once would have been sufficient. And your computer was acting up on you. And you were breaking up there. I was assuming your computer wasn't responding as quickly as it should have been. Oh, I didn't know that happened. Yeah, on campus, it's getting really windy outside and really dark. So I guess the cloud covers are getting really severe. I'm betting, even though it says it's 72 degrees outside, betting it feels a lot colder than that because people are running around looking like that. So. And the temperature out at the airport isn't necessarily the temperature where you're at. Temperature at the airport is usually hotter or colder. Okay. I'm gonna go ahead and get started. So there we go. So I believe we finished up with the composition of functions. And now we can move on to one-to-one functions and their inverses. Did we start this?
No, this is pretty much where we stopped.
Yeah. One of my other college algebra classes, we've already gotten, of course, they use a different textbook in that course. So we go a little faster in there because in that class, we don't cover everything we cover in here. Okay. One-to-one functions. First thing we're going to do is discuss what a one-to-one function is, and then determine if a function is a one-to-one function. We're going to obtain the graph of the inverse function from the graph of a one-to-one function. But first, we're going to talk about what an inverse function is, and then verify that a function is the inverse. So you verify that two functions are inverses of each other, and then find the inverse of a function that is defined by an equation. So if you have an equation y equals 3x plus 5, what's the inverse for that function? Or you have a function y equals x divided by x minus 3. What's its inverse? A one-to-one function. A function is one-to-one if any two different inputs, meaning two different x values in the domain, correspond to two different y values, two different outputs in the range. So if you have two different x's, you will get two different y values. Not write it down in the other class. A function is 1 to 1. I'm writing too small, aren't I? A function is 1 to 1 if each x value is paired with a distinct y value. Not only is it paired with exactly one y value, but it's the only x value with that y value. So if 3 is paired with 2, 2 is only paired with 3. So one of the effects here of it being a function is that the x values don't repeat. And one of the effects of a function being one-to-one means the y values don't repeat. That's not part of the definition. That's just an effect of what it means to be a function or a one-to-one function. So a one-to-one function means that each x value, so if you look at it in a mapping, each of these x values goes to a specific and distinct y value.
So in a situation where it's like y equals x, that would be counted as like a one-to-one.
Yeah, y equals x.
That would be
1
like an
plus
example.
2, 2, 3, 3, 4, 4, 7.9, 7.9. Yeah.
Okay, thank you.
Y equals x is a one-to-one function. Where x squared is not. X squared is a function that is not one-to-one. Because f of 2 equals f of -2 when f of x equals x squared, because 2 being squared is the same thing as -2 being squared, because they both equal 4. That is what this is saying can't happen for it to be one-to-one. So x squared is not a one-to-one function, because I have 2 different x values going to the same y value. Well, now each x value goes to its own y value. That's what I mean by, that's what the word distinct means. So each of these x values have a y value that's assigned to them, and no other x value has that y value. If 3 has 2 as its y value, no other x value will have 2 as the y value. One-to-one functions are a subset of functions, and they're a very special subset because certain things happen with one-to-one functions that don't happen with other types, with functions that aren't one-to-one. And one of them is that one-to-one functions, their inverses are functions. X squared has an inverse, but that inverse is a relation. It's not a function, because the inverse of x squared is plus or minus the square root of x, which means you get 2 y values for each x input. But anyway. We'll look at that more closely. And hopefully it'll become clear. So I like this graphic because the one in the middle is just a typical function. Right? Each x value only goes to one y value over here, but they can go to the same y value. All of these could have gone to the same y value, or all of them go to different y values, but 2 of them go to the same y value, or all of them go to different, but we weed those out. When each X value goes to a unique Y value, a distinct Y value. So X of 1 only is the only X value that goes to Y sub 1. X of 2 is the only X value that goes to Y sub 2. X of 3 is the only X value that goes to Y sub 3. Then those are one-to-one functions, which is a subset of functions. Now, this is not a one-to-one function because I have two X values going to the same Y value. And then the third graphic here shows a relation that is not a function because this X value goes to two different Y values. And you can't, that contradicts the definition of a function, so it's not a function. X of 1 has two images in Y, where for it to be a function, each X value can only have one image in the Y. X values can share an image, but each X value only goes to a single Y value. And over here, each X value goes to a single Y value, and it's the only X value that goes to that Y value. Have to do my little stuff. All right. Is this function one-to-one?
No,
Why not?
because two X values have the same Y value.
Correct. For it to be, all right, it's a function because we only have one arrow coming off of all of these. But for it to be one-to-one, each of these Y values can only have one arrow going to it. 35 has two arrows going to it, which makes it not one-to-one. And that's what they say. We have two different inputs going to the same output. Is this a function? So is -5 paired with any other number other than -3? Is -3 paired with any other number other than, is that a -3? No, that's a +3 and a +5. Is 5 paired with any other number other than -3? Is 3 paired with any number other than -2? Is 1 paired with any other number other than -1? Is -1 paired with any other number other than 0? Is -3 paired with any number other than 2? So I'm looking, not only am I looking, is it a function, do each X values go to only one Y value, but does each Y value have only one X value that comes to it? In other words, it's a set of monogamous pairs. The function is one-to-one because every distinct input corresponds with a different output. Now we have the horizontal line test. The vertical line test determines if it's a function or not. The horizontal line test determines if it's a function or not. I mean, a one-to-one function or not. All right, if in this case, this function is not one-to-one because I have two different x values that go to the same y value. And that y value forms a horizontal line. If the horizontal line hits it more than once, it's not one-to-one. So for it to be a horizontal line, for it to be a one-to-one function, then the graph, then the horizontal line intersects the graph at most at one point. Since it intersects it twice, it's not a one-to-one function. It is a function, but it's not one-to-one. So in this case, we look at the two different graphs. For f, the graph is of x to the sixth power, which it's a type of parabola. Whenever you have parabolas or parabola-like functions or graphs, then they're not one-to-one. Because we have two different y values, two different x values that give the same y value. So all except for one horizontal line that hits this graph will hit this graph in more than one place. So it's not one-to-one. X to the fifth, this is the graph of x to the fifth. It's very similar to x cubed. But every single horizontal line will intersect this graph at exactly one point. So if I keep drawing horizontal lines through it, it's only going to hit it once.
What about during y equals 0? Does that not count? Is that not applicable?
Say again?
Essentially when, actually, never mind. That's me being stupid. Don't worry about it.
Yeah, you can look at the x-axis. It'll hit it only once.
Yeah, no, I was thinking for some reason that all of it was on 0. It's just too small to really calculate it.
Yeah, it is so close to 0 that it looks like it is 0.
Yeah, that's what I was saying. That's me being stupid for a second. That's just my eyes.
So, well, because of the thickness of the line, you can't show how close it gets to the x-axis without actually being. So it does look like it intersects the x-axis. It becomes the x-axis, but the only place it equals 0 is when x is 0. Because as soon as you get off of 0, you're no longer at 0, either in the negative direction or the positive direction. You're going negative, automatically you're below the x-axis. And if you go to the right of 0, immediately you're above the x-axis. So. Because every horizontal line intersects the graph at exactly once, intersects the graph exactly once, the function is one-to-one. I would have used x cubed instead of x to the fifth, because then that separation there is more evident. All right, if a function is increasing on an interval, then the function is one-to-one on that interval. And if a function is decreasing on an interval, then the function is one-to-one on that interval. We back up here. This is increasing over its entire domain. But this function is always increasing. So one-to-one functions are either always increasing or always decreasing. But if we look at the graph of a function, say it goes something like this, then I can look at intervals like from A to B here. In this interval, the graph is increasing. So in this interval, the function is one-to-one, even though the function itself is not. As long as I restrict my domain, then I have an increasing function. And conversely, if I define an interval and I look inside this interval, what is the function doing in that interval? Well, the function is decreasing. So that means the function is one-to-one in this interval, even though it's not a one-to-one function. The function itself is not one-to-one, right? Because I can draw a horizontal line through here and it hits the graph more than once. But in this interval, it only hits it once. And in this interval, it only hits it once. So in these intervals, it is one-to-one. So if I have a function that isn't one-to-one, and I need it to be one-to-one, then I can redefine it by restricting its domain. And we'll look at that a little later. Any questions on this? I think this is pretty straightforward, but then math is my life. Okay. Suppose y equals f of x is a one-to-one function. The correspondence from the range of f to the domain of f is called the inverse function of f. The symbol f to the negative 1. So how we state this is not f to the negative 1. This is f inverse. So we're just saying, so we can say this, so instead of having to write the words, the inverse function of f, we write it this way. And I will very often say f inverse or the inverse of f. And so if f is a one-to-one function, then f has an inverse function, f inverse, and x will equal f inverse of y. So it's going to take the range back to the domain. This takes us from the domain to the range, where this takes us from the range back to the domain. So for the inverse function, the range becomes the domain, and the domain becomes the range for the inverse function. The graph of a one-to-one function and the graph of its inverse are symmetric with respect to the line y equals x. And here's an example. Notice the points. Can you read those? Can you read that graphic? Notice the points on f of x. And notice the points on f inverse. What happens to the x and y values? Tell me.
They switch.
They switch. The X's and Y's switch. So if this was -2, -1, then this down here is -1, -2. If this is -3, well, if this is -1, 1, then this over here is 1, -1. So you're just switching your X's and Y's. Because this domain became the range over here, and this range over here became this domain. So if we follow that, this point here is -2, -1. So if I switch my -2 and -1, I get -1, -2, which is oh, I put that right there where I need to put my point, which is right here. And this point, which is 1, 0, now becomes 0, 1, which is this point here. And this point is 2, 2, and switching the 2's gives you 2, 2. So this point, so my graph here looks like this. And if you notice, what they start out with is saying graph y equals x. So here's y equals x. And notice where they intersect. Notice where the two graphs intersect. They intersect on y equals x. So not only are they going to be symmetric with respect to the y equals x, that if they intersect, they're going to intersect on y equals x. Inverse functions do not always intersect, but when they do, it's on y equals x.
So in a situation where it's like y equals x cubed, would they still intersect on y equals x?
Correct.
Or would they? Okay.
Because x cubed kind of looks like this. And the cube root of x, something like that. And so they'll intersect at 3 points. -1, -1, 0, 0, and 1, 1.
Gotcha. Okay. Thank you.
Not all of them do that,
But if they do,
but this one does. Now, we're going to go through an example where you're going to wind up with a graph that looks like this. And they don't intersect, but they're still going to be symmetric with respect to the y equals x. And then the rest of this is doing what I had done, which I found these 3 points, and then just drew the lines in. Oh, I forgot. Our next slide is slightly off from what I had written. Now, because of the nature of the inverse, these x values take me over to these y values. But for f inverse, these y values are the x values for f inverse. So this range became the domain for F inverse. And it brings us back over to the domain of F. So now this is the range of F inverse. So because we're going to end up going backwards, that means our domain and range is reverse. So the domain of F becomes the range of F inverse. The domain of F becomes the range of F inverse. And the range of F becomes the domain of F inverse because of the direction we're traveling. Well, where we're coming from is the domain, and where we end up is the range. And since these are one-to-one functions, boom, that's how it happens. All right, and so, whoa. And so I start, like if I start with a specific X value here, and I'll come over to a specific Y value over here. So I'm gonna call this X sub 1 and this Y sub 1. Now this Y sub 1 becomes the X value for F inverse. And when I do F inverse on this Y sub 1, it brings me back to this X sub 1. So F and F inverse, they undo each other. You come back to where you started from. And that's what happens with inverses when you compose them. If I do F inverse on the F of X, I will wind up at X. If I do F of F inverse of X, I wind up on X. So they undo each other. You end up just like this slide over here. I go over here and then I come back again. I come over here and then I go back again. I wind up at the same value I started at. Because of the nature of the inverse functions, that's what happens. Which is very helpful in other things that inverse functions tell us. All right, to verify that these are inverses is you do those compositions. You do G, I always start with G of G inverse, but they do it the other way around. To me, it makes more sense to do G of G inverse and then G inverse of G, but they do it the other way around. It's a matter of preference. And so since G of X is X to the 5th, and G inverse is the 5th root of X, then G inverse of G of X is the 5th root of X to the 5th power, which is just X. And please notice the stipulation they put down there. If there are numbers you can't use in G, there's numbers you can't use in that composition. Now, letter B. The second half. The first half is doing G inverse of G, and now we're going to do G of G inverse. And since G inverse is the cube root, the 5th root, we're going to do G of the 5th root of X. And G is to the 5th power. So we're going to take the 5th root of X and raise it to the 5th power, which just gives us X. And again, the stipulation that X has to be in the domain of G inverse. Which when you have fraction functions, that becomes very important when X is in the denominator. that becomes very important. Because if I can't use it in G inverse, I can't use it in the composition. Because there's no corresponding value in G inverse for that number. So for letter B, we're going to do the compositions with these two functions. So we're going to put 4x minus 7 in place of x here and simplify it. And that's what they did. They put the 4x minus 7 in place of x in the 1/4 of x plus 7. So they get this expression here. And then what we're doing, we're going to combine in here first. Since we're adding these two expressions, we can drop that parentheses, and this is just 4x minus 7 plus 7, which is 4x. So 1/4 of 4x is x. So that verifies it going one way. Now we need to go the other way. And we're going to put 1/4 of x plus 7 in for x in 4x minus 7. And so it's 4 times 1/4 x plus 7 minus 7. And what we're doing here with these brackets and this, that just means we're going to be multiplying 3 things together. So 4 times 1/4 times x minus 7. I'm not going to use the derivative property here. I'm just going to do straight multiplying. Because I have 2 things in here. I have A and B. So, and the reason I'm stressing this is because people really don't understand this part. This is just 4 times A times B, where B is the expression x plus 7, and A is the fraction 1/4. So we have 4 times 1/4, which is 1. So what this side of the plus sign is just x plus 7. Because we're just doing 4 times 1/4, which is 1. So we just add x plus 7. And so these two go to 0. So it's just x. For all x in the domain of F inverse. And the domain of F inverse is all real numbers. So this is true for every real number. Now, doing the same thing here. Now, these 2 questions for what values is x? For which values of x is that true? And so you have 2 questions about those 2. So that's this part here. That's this part here. But we're getting more specific, other than just saying the domain of F inverse or the domain of F. We want to know specifically what values or what values we have to exclude. So since f of x is the inside function, then x can't be -2 because -2 plus 2 is 0, and we can't have that. So this will be true for all real numbers except for -2. So x cannot equal -2. And something similar here, F inverse, we can't use 0. And so the domain here is, or the restriction is that X is not 0. But we need to verify that these two statements are true. So they looked at those two domains, and those two domains tell us what values of X you can use. All right, so we're going to put F inverse, put 1 over X plus 2 in for X in F inverse. So 1 over a fraction is the reciprocal of that fraction. So 1 over X plus 2 is just X plus 2. So we have X plus 2 minus 2, which is X, because 2 minus 2 is 0, and that just leaves us the X, provided X does not equal -2. Now, obviously, I can put -2 in for X, but because I can't put -2 in for X here, for F of X, I can't use it. Because how the function is set up. Now going the other direction, we're going to put 1 over X minus 2 in for X in the F function. So I'm going to simplify my denominator, which this minus 2 and this plus 2 goes to 0, so my denominator is just 1 over X. So 1 over a fraction is a reciprocal of this fraction, and the reciprocal of 1 over X is X. Boom. We verified it, provided X is not 0 in this case, because I can't use 0 here, I can't use 0 here. Even though X is part of 0 is part of the domain of X, it's not part of the domain of that composition. How many people remember how to find inverses? I do, because I teach it every single year. Y'all remember how to find inverses? You're given that equation and you're given that function. And what we need to do is rewrite that function as y equals 3x minus 5. Anyone recall how to do that?
Don't you solve for X at that rate?
Well, you need to do something first. But technically, that's what you're going to end up doing. But what the first thing we do is we interchange the x's and y's. So this becomes x equals 3y minus 5, and then we solve for y, which is basically the same thing you said, but it's not a function. It's not that's not the inverse function. That's just rewriting this into a different function.
Gotcha.
I mean, an implicit form of the function. This is an explicit form of the function. And but this gives us the implicit form of the inverse function. And so we want to solve for y so we can state the explicit form of the function, where we get the y values every time we put a number in for x. So we add 5 to both sides, so that gives us x plus 5 equals 3y. And then, all right, there's two ways of looking at this. One way is to divide by 3, and we get x plus 5 divided by 3 equals y. So now we have the explicit form of the equation. And so now this is our F inverse. Now what they do, they say divide by 3 and they multiply by 1/3. I don't know why they say one word and they actually do something else. Because this is not the same. Semantically, this is different than dividing by 3. This is multiplying by 1/3. The end result is the same. 1/3 of 3 is the same as dividing 3 by 3. So they come up with this one here. Even though they use the same language I did, but they wrote it this way. So replace the y with, replace the f of x with y, and then you interchange the x and y, and then you solve for y. And please notice here, all they did was switch the sides of the equal sign. So they would have y on this side. You don't need to have y on that side. Because then they're doing the exact same thing I did. So they add 5 to both sides, and then they're going to say to divide by 3 on both sides, but they multiply by 1/3 on both sides. And then replace the y with f inverse. So you get the inverse of x. The f inverse of x is 1/3 x plus 5. But I like to write it this way. Sometimes it's easier to see what's happening there with that. And then they tell you to graph it. Okay. So graphing it, graphing the two functions, I like to choose 3 or 4 numbers. And so this will be for f of x. So I'm going to do -1, 0, 1, and 2. So I'm going to do 4 numbers simply because I can. So -1 times 3 minus 5 is a -8. 3 times 0 minus 5 is a -5. 1 times 3, or 3 times 1 minus 5 is a -2. And 3 times 2 is 6, and 6 minus 5 is 1. And now f inverse of x to get my x's and y's. My y's from my f of x, I'm going to make those my x's, because that's what happens. And now I'm going to verify that -8 gives me -1. So I'm going to put -8 in the numerator. -8 plus 3 is a -5. -8 plus 5 is a -3. And -3 divided by 3 is a -1. -5 in here, -5 plus 5 is 0, and 0 over 3 is still 0. -2 plus 5 is 3, and 3 divided by 3 is 1. and putting 1 in here, I get 1 plus 5 is 6, and 6 divided by 3 is 2. So my x's and y's did flip-flop. My x's over here are my y's over here, and my y's over here are my x's over here. So it verifies that they are inverses. And then to graph these, we graph those points, -1, -8. So -1, -8 down here, and then 0, -5, 1, 2, 3, 5, and then 1, -2, 1, -2, and then 2, it's at 1. And then here I start at -8. So 8, -1, down here. And then at 5, 1, 2, -5. And then at -2, it's at 1. And then at 1, it's at 2. Not wrong scale. So we have that line, and we have this line, and where they intersect will be on the line y equals x. Just realized I didn't get all my points. Yeah, I'm just gonna mess up. All right. And they found different points. But basically, they got the same graph I did, even though theirs is neater. It's still the same graph. And if I had graph paper up there, I mean a grid pattern up there, I'd be done. Classroom's getting warm up. Okay. And then we have the symmetry with respect to the y equals x. And so this is just the steps we were doing. You replace the f of x with y, and then you switch your x's and y's. Where there's an x, you put a y, and where there's a y, there's an x. And then you solve for y. And that gives you f inverse. And then you check your result by doing the two compositions, f inverse of f and f of f inverse. Find the inverse of x plus 1 divided by x minus 2. Well, we write this as y equals x plus 1 over x minus 2. And then where there's an x, I put a y. And where there's y, I put x. And this gets a little tricky, but not difficult. And we solve for y. We have two y's in this equation. Well, that's going to be easy to deal with. First thing we need to do is to multiply both sides by y minus 2. So this denominator disappears. And then we do the distributive property to get xy minus 2x. And now, whenever I'm trying to solve for a variable, I want that variable on one side and everything else on the other. So I'm gonna subtract y from both sides, and I'm gonna add 2x to both sides. So the 2x will disappear over here, and it'll appear on this side, and the y will disappear from this side and reappear over here. So we have xy minus y. I can't do that subtraction directly because these are two different terms. This term has an x and a y in it. This one only has an x. I mean a y. And then 2x plus 1. So we added the 2x to both sides and subtracted the y from both sides. Now here, I have y as a factor of both these two terms. So I'm going to factor that out. So I'm going to factor y out. So I just have one y, right? Now I have y times an expression. Well, if I divide both sides by this expression, then I'll have y equals. There I have y equals. Because if I divide by x minus 1, these go to 1 and it disappears. And I just have x plus 2, 2x plus 1 divided by x minus 1. And then I just replace y with f inverse of x, which is what they do on the next slide. And so there's my inverse function. And now you need to verify. Yeah, you have fractions here. They're fun. It's a puzzle. It's playtime. Oh, we're screaming profanities at me. So I'm going to put the fraction x plus 1 divided by x minus 2 in for x in f inverse. So wherever there's x in f inverse, I'm going to replace it with this fraction. Here, I'm going to multiply in the numerator. I'm going to multiply in by that 2, so I get 2x plus 1 plus 2 divided by x minus 2 plus 1 plus 1 divided by x plus 1 divided by x minus 2 minus 1. Now I'm going to multiply everything by the common denominator. I'm going to multiply each term by x minus 2. That's like multiplying numerator and denominator by x minus 2. I'm multiplying by 1. But this is doing the distributive property while I'm doing it. So the reason we do that is so the denominators of the in the fractions disappear. So my numerator up here is 2x plus 2 plus x minus 2. And my denominator, well, this is a minus 1 times x minus 2, so that becomes a minus x plus 2, because I'm multiplying each of these by the minus 1. So my numerator, my denominator becomes x plus 1 minus x plus 2, which is what they show right there. They don't show this process. In my denominator, I have a negative x, I have x and negative x, those go to 0. In my numerator, I have a positive 2 and a minus 2, those go to 0. So my numerator is 2x plus x, which is 3x. My denominator is 1 plus 2, which is 3. So now I have 3x over 3, and guess what? That's x. And I put the stipulation that x can't be 2 because I can't, because that's the domain of the inside function. Okay? Okay. Now doing the other one isn't as difficult as this was. Not that this was hard or anything. So now we're going to put 2x plus 1 divided by x minus 2 in place of x in this fraction. Now we don't have to worry about multiplying in by 2 before we do things. Now I'm going to multiply the numerator by x minus 1 and the denominator by x minus 1, and that means this fraction gets multiplied by x minus 1, and this plus 1 gets multiplied by x minus 1. This gets multiplied by x minus 1. This fraction does. As a matter of fact, these two fractions become 2x plus 1. And multiplying a minus 2 times x minus 1 becomes a minus 2x plus 2. Which is what they have there. So they did the same thing they did up there, they did down here. And notice in the denominator, we have a 2x and a minus 2x. And in the numerator, we have a plus 1 and a minus 1. Those go to 0. So my numerator is 3x. My denominator is 3. Look familiar? Okay. And so 3 over 3 is 1. So that just leaves us x. And we can't use 1 because I can't use 1 here. So the domain of f becomes the domain of x of the composition, of this composition. And the domain of f inverse becomes the domain of the composition. And in this one, the domain of f became the domain of the composition. Find the inverse of x squared plus 1 where x is greater than or equal to 0. Please notice we have a restricted domain. So we need to take that into account when we look for finding its inverse. So first of all, we need to determine that f is a one-to-one function. Because x squared plus 1 is not 1-to-1. X squared plus 1 looks like this. which is not one-to-one because any horizontal line I draw through it hits it in two places. But since my domain is restricted, to only non-negative numbers. So that means the graph of it is going to look like this. It's only half the parabola. And it includes this, the absolute minimum point. So this function is increasing over its entire domain. So it is a one-to-one function. So yeah, I can find the inverse of this. I have a restricted domain, which means I'll have a restricted range. The range here is from 1 to infinity. Okay, so it's all values of y greater than 1 or greater than or equal to 1. So that becomes my new domain. X has to be greater than or equal to 1. In my F inverse, my F inverse domain is the range for this. The range for this is y is greater than equal to 1. So the domain here is that x is greater than or equal to 1. My domain here was x is greater than 0. So that means my range is going to be y is greater than or equal to 0. Right? This domain became the range. I'm just switching the x's and the y's. And this range became the domain, just switching the x's and the y's. And so now I switch my x and y. So now I have x equals y squared plus 1. And I solve for solve for y. That means I need to subtract 1 from both sides. So I get x minus 1 equals y squared. Now I take the square root of both sides, but normally we say plus or minus the square root of x minus 1 equals y. But y has to be positive for 0. So that means I dropped the minus sign here. And so the square root is only the positive square root. And since x begins at 1, 1 minus 1 is 0. And so square root of 0 is 0, which is in the range that we discovered. So that's my inverse. F inverse of x equals that. All right, this is the square root function that has been horizontally shifted 1 unit to the right. So x squared goes like this. The square root of x minus 1 goes like that, where y equals x goes shooting between them. But they're still symmetric with respect to that line. So whatever this point is, I switch the x and y, that point will be over here. So, yeah. So it has an inverse function. Because it's 1-to-1, it will have an inverse function. All functions that are 1-to-1 have inverse functions, or have inverses that are functions. All functions have inverses, but they're not always, their inverses are not always functions. All right, in that equation, x has to be greater than 0 or equal to it. And so then we solve for x. Solve for y explicitly. And because y has to be greater than or equal to 0, only one solution for y is obtained, and that's the positive numbers, like I had already explained. They didn't go through the process of finding this, like I did. So they have the same function there. And checking is putting those in to see that you do, right? So the absolute value here, the square root could be a positive number or a negative number. So we say it's the absolute value of x. But since x is greater than 0, then it's just x. Because if x is greater than or equal to 0, its absolute value is just whatever x is. And doing the composition the other way, when you square a square root, it's just x minus 1 and then plus 1, which just gives us the x. They didn't show that process. And again, x has to be greater than 1 or equal to 1. And there's the graph of the two things. This is the point 1, 2, and this is the point 2, 1. Because 2 minus 1 is 1, and the square root of 1 is 1. And 1 squared is 1, and 1 plus 1 is 2. Questions? Now we're going to talk about exponential functions. We're not going to get too far into them, but we'll get a little bit. Well, today anyway. We'll get further into them on Monday. But right now, we're going to, first of all, we're going to talk about what exponential functions are. And we're going to graph exponential functions, define the number e. E is an italicized e. And if you see it in a textbook or whatever, the e is italicized, however you say that word. It's an irrational number. It is approximately 2.7. I don't know what it is exactly. A French mathematician back in the 1800s, or it could have been the 1700s, I don't know. I think it was 1800s. He did a lot of stuff with sets and with pathways. If you're a computer programmer, a lot of the work he did with pathways you use in computer programming. So he was very influential and very smart. But he discovered this number. It's an irrational number. And there's a formula for finding that number. And the reason we assign it the letter E is because his name is Euler. But you're going, how do you get E out of Euler? Well, because he spelled his name this way. It's French. I don't know. And they pronounce it Euler. Some people pronounce it Euler or Euler or some weird way of pronouncing it. I've always heard it called Euler. Like Houston used to have the Houston Oilers. Okay. And then saw equations involving the number, the exponential function e to the x, when you get into calculus, is a very funny number. It's very funny or special function. Some things happen to it with it that are really interesting and useful. It's a useful engine. So evaluating these powers of 3, so 3 to some power. And please notice these numbers here, 0.7, 0.17, 1.73, 1.732, and the square root of 3. Those exponent numbers are increasing up to the square root of 3. So those numbers are getting closer to the square root of 3. So the exponent is increasing. So that means x to those numbers is going to be increasing. Whoa, thank you. And so x 3 to the 1.7 is that number. 3 to the 1.73 is that number, approximately. And please notice that these numbers are getting larger, but they're slowing down. The difference here is quite large, where the difference here isn't as large. And then the difference here is even smaller. So if we went down to the next decimal place and did 3 to the 1.73, whatever, it would get even closer to this number. So those are exponentials, where the thing that's changing is the exponent. And the base remains the same. The base is constant. These are some, I taught these as I call the rules for exponents, or the exponential rules. It's the theorem, it's the laws of exponents. This is always true of all exponents. Okay? When you multiply like bases, you're adding the exponents. When you're raising an exponent to a power, you're multiplying the exponents. When you're raising a product to an exponent, then each factor gets hit with the exponent. S to any power, including 0, is 1. 1 to the 293,000th power. That means you're multiplying 290, however many number I said. You're multiplying that many ones together. Multiplying 1 times 1 times is still going to be 1. So 1 to any power is 1. The negative exponent just means you're doing the reciprocal. I like to think of saying it's in the wrong place in the fraction. So it goes downstairs and the minus sign goes away, because it's where it's supposed to be. If this was s, if this was 1 over a to the negative s, then that means it needs to come up to the numerator. Okay. But 1 over 1 to the s power is the same as 1 over a to the s power. So 1 over 3 squared is the same thing as 1/3 being squared. That's very helpful. And any number raised to the 0 power, except for 0, is 1. This is a truism. The only number it's not true with is 0. I think it's undefined or a special kind of undefined. Or it may be just 0. I always thought it was undefined. 0 to the 0 power. Okay. We will be using these a lot when we start doing exponentials and start doing logarithmic functions or logarithmic expressions. Logarithms are exponents, so we use these rules with logarithms. All right, definition of exponential growth. Well, the definition of an exponential function is basically the same thing. An exponential function is a function in this form. F of x equals c times a to the x, where a is a positive real number. That means a is greater than 0, but not equal to 1. So the positive real numbers taking out 1. Because if I just put 1 here, then x1 to the x power is just 1, and 1 times c is c, so that just makes it a constant function, not an exponential function. The domain of f is the set of all real numbers, so I can use any number here. I can use 0. I can use 235,000. I can use a negative 362. I can use pi. I can use negative 3 pi times negative 3 pi minus 4. So I can use any number here. Rational, irrational, negative, positive, 0. C can't be 0 because if C is 0, this is just 0. So that makes this a 0 function, not exponential. And C, again, can be any real number. The domain of F is the set of all real numbers. The base A is known as the growth factor, and when you're talking about exponential growth. And because f of 0 equals c, because a to the 0 power is 1 and 1 times c is c, c is called the initial value. X equal to 0 for exponential growth. 0, exponential growth talks about over time, where your x values are time. So time, when we talk about time, we start at time 0 and grow from there. So that's why at 0, you have c as being the initial value. So if you're looking at the population of an organism, at time 0 is how many organisms you have to start with. So if it's mold, how many mold things you have in there? If it's bacteria, how many bacteria do you have in there? If you're looking at a fish population, how many fish are in the initial population that you're starting with? That's what the C value is. That's the initial value. That's your starting point. Okay. Exponential function. If f of x equals c times a to the x power, where a is a positive number and a is not equal to 1 and c doesn't equal 1, if x is any real number, then f of x plus 1 over x, f of x equals a, what you're multiplying by. Or f of x plus 1 is a times f of x. Since x is the exponent, and it tells you how many times you're multiplying by a. If I multiply by another a, then that's just multiplying, then that's just increasing your exponent by 1. All right, this is what the function is. So this becomes a times c times a to the x, which equals c times a to the x. Multiplying like bases, I add the exponents. So this becomes c times a to the x plus 1, right? I'm adding 1 to x, so that's 1 plus x, which is f of x plus 1. Because f of x plus 1 is c times a to the x plus 1. So, boom. And then I divide both sides by f of x, I get this. So this ratio, you start looking at consecutive outputs. Consecutive outputs differ, the x values differ by 1. You put them in a ratio, they should equal the same number, a. So at f of 2 and f of 3, they should equal a. And f of 7 being divided by f of 6, that should equal a. F of 3 is c times a to the third. F of 2 is ca to the second power. So those go to 1. And this is just a to the third divided by a squared, which is a, right? When you're dividing like bases, you subtract the exponents. 3 minus 2 is 1. And here we're going to have c times a to the 7th power divided by c times a to the 6th power, which those go to 1, which is just a to the 7th over a to the 6th. Again, you subtract the exponents, that gives you a to the 1st power, which is just a. So as long as you're talking consecutive outputs, those ratios will be a, the base, the growth factor. Now, we want to determine if these are linear or exponential or neither. Since they have 3 examples, guess what? You have 1 of each. So to do this, we look at our average rate of change between consecutive outputs. So my changes here are 1, 1, 1, and 1. My changes here are this is a -4, this is a -4, this is a -4, and this is a -4. I subtract 4, I get 2. I subtract 4, I get -2. I subtract 4. And so my average rate of change is the change in the y's over the change in the x's. So that's a -4 over 1, a -4 over 1, a -4 over 1, a -4 over 1. So this over that, this over this, this over this, that over this. And they all equal -4. So my changes are constant. If my average rate of changes are all the same, then it's going to be linear. But I want to look at my -6 over -2, which is a +3, and -10 over -6, which is a +5/3. None of these are the same. They all have to be the same for it to be exponential. They all have to be the average rate of change needs to be the same for it to be linear. So this one is linear. And I could have stopped at this point, because if it's linear, it cannot, there's no way it will be exponential. There's no linear function that is exponential and no exponential function that is linear. It does not happen. So now we look at letter B. Again, all my changes here are 1 and 1. My change here is a -54. My change here is a -18. My change here is a -6. And my change here is a -2. And so dividing each one of these by 1, I get these numbers back again, and none of them are they're not the same number, so it's not linear. Okay, just because it's not linear does not automatically mean it's exponential. So now I do the ratios, the previous over the former. So 27 over 81, which reduces to 1/3. And then 9 over 27, which reduces to 1/3. Looking good. And then 3 over 9, which reduces to 1/3. And this one is 1/3. So they all the ratio of the former, I mean the next over the former, they all equal the same number there, so it's a constant ratio. So it's exponential. All right. With linear, this -4, the -4 is the slope. So I can write this as y equals mx plus b. The slope is -4. The b value is what it is when x is 0. And so that's +2. So this is the function. This is the function. I'm not giving. I'm just going to say y equals that. Negative 4x plus 2. Here, this is my a value. So a is 1/3, and that's what I'm raising to the exponent x. And when x is 0, that gives me the initial value, 27. So this is going to be a 27 here. So this is the exponential, 27 times 1/3 to the x power. On letter C, we do the same thing. Again, each one of these and the x's, they change by 1. I add 1, I add 1, I add 1, I add 1. And here they're going to change, this changes by what? 3. And then this changes by 4, and this changes by 5, and this changes by 6. So 1/3, 1/4, 3 over 1, 4 over 1, 5 over 1, 6 over, so these are my changes. They're not all the same number, so it's not linear. So now I do the x, look to see if there's the ratios of the consecutive outputs. So that's 7/3, 11/7, 16/11, 22/16, which reduces to 11/8. All of these are different numbers, so it's not exponential, so it's neither. Whenever it's IE or EI, I always looks wrong to me. No matter which way it's put. And they go through and do the same thing. So for each function, compute the average rate of change, which is the change in y over the change in x. And if the change is constant, then the function is linear, and you don't need to do anything else. If the ratio of consecutive outputs is a constant, like we got 1/3 on the second set of data, then the function is exponential, and if neither happens, then it's neither. So they did the average rate of change, and they did the consecutive outputs, the ratio of the consecutive outputs, and they got the same numbers I did, I believe. And it showed that it was linear. And then they saw that so that's the slope is m. I mean, m is -4. And at 0, the b value is 2. And so they got the same equation I did. F of x equals a -4x plus 2. On the second one, the average rate of change for the consecutive outputs it wasn't the same. And so then they did the ratio of consecutive outputs, and they all equaled the same number, so it was a constant. The ratio of consecutive outputs was constant. And so it's not a linear function, but it is a input. It is a exponential function. And so, okay. And then we can rewrite this as the way I've done it. So A is 1/3. And when X is 0, C, the function is 27. And so we have this. And we're about, what, a minute after? And then the third one, I'm just gonna, neither one of them gave us a constant number. And so it's neither. And then this is a slide we'll start on next time. Okay. Any questions for me? I didn't mean to turn that off.